Today it's my pleasure to introduce our speaker, Alea Ahmed. She's an associate professor of both mechanical engineering and integrative physiology at the University of Colorado Boulder. She did her undergraduate in mechanical engineering at the University of Cairo and her PhD at the University of Michigan doing postural control with James Ashton Miller, and a postdoc at Cambridge with Daniel Walpert, looking at how you make decisions in movement, and she's successfully put that together in our own research program, and we'll be talking to you about that today. So thank you, Leah, and take it away.
All right, thanks, Lena. Thanks for the invitation. It's great to be here today. Thank you guys for coming. So I went on sabbatical a year ago, maybe 2 years ago now, and sabbaticals are great for many reasons. But one reason is that it really gives you a chance to just sit down and think about one idea. Really just focus on one question and give it your all. And the question that I really spent a lot of time thinking about was the speed of our movements. So why do we move at the speed that we do? Why do some people move slowly? And why do some people move fast? And do people who reach slowly also walk and talk slowly? And do fast talkers also reach fast and walk fast? And this isn't idle curiosity, because the speed at which you move can actually say a lot about an individual's health. Okay, so for example, in Parkinson's disease, the cardinal symptom is bradykinesia, or slowness of movements. So I thought, if I want to understand the neural determinants of movement speed, then Parkinson's disease is a reasonable place to start. Now, Parkinson's disease is a disease of the basal ganglia, and it arises from loss of dopaminergic neurons in the substantia nigra, a part of the basal ganglia. And these neurons release a neurotransmitter called dopamine to various parts of the brain. So in a study back in 2007, John Krakauer and Pietro Mazzoni investigated reaching movements in individuals with Parkinson's disease. And so they had PD patients and healthy age-matched controls. They asked them to make reaching movements to targets on a screen at a prescribed velocity. And this study had surprising results for two reasons. One, when sufficiently motivated, the Parkinson's patients could reach just as fast as the healthy age-matched controls. Okay? And when they reached just as fast, not only could they reach just as fast, but they could also reach just as accurately. And this is surprising because what was thought to be the cause for slower movements in Parkinson's disease, at least partially part of the cause in people with Parkinson's, was that they could move just as fast, but they would move less accurately. Okay. But in this case, they saw that Parkinson's patients could move just as fast when sufficiently motivated, and they did so just as accurately. So the common reasoning for why PD patients were moving more slowly was in some way debunked. It seemed that PD patients were moving slowly because they chose to. Okay? And I thought this was really interesting because, as I mentioned earlier, the main pathology in Parkinson's disease is loss of dopaminergic neurons, which produce a neurotransmitter named called dopamine. So to understand why this is interesting, let's look a little closer at dopamine. So the dopamine neurons in the basal ganglia are located in the substantia nigra and the ventral tegmental area, shown here in areas A8 through A10. And these neurons send axons along a long-distance trajectory that could influence brain activity in many areas. So from the striatum all the way to the frontal cortex, an area that's critical for decision-making. What this means is that dopamine is not just involved in movements, but also plays a role in decision-making. Okay? So what role does dopamine play in decision-making? In a series of pioneering and now classic experiments, Wolfram Schultz recorded from single dopamine neurons in the midbrain of monkeys as they learned a Pavlovian conditioning task. And in one variant of these experiments, a thirsty monkey sat in front of a water spout, and at unpredictable intervals, a tone was played. Okay? And a drop of juice would be provided to the monkey shortly after the tone was played. So initially, if you look at this top plot, the dopamine neurons would respond to the unexpected juice reward, indicated here as R, and they would increase their firing rate. Okay? Let's see if I can move it up here. So here is the unexpected tone. Well, they would get a tone. Here's the unexpected reward, and then you would see an increase in firing rate here. Is that showing up? Great. Okay. So, but as the monkeys learned to associate the stimulus with the reward, the dopamine neurons began to respond to the tone that was predictive of the reward. So if you look at this middle plot here, here is the stimulus, the tone, and now here you see the increase in firing rate, even though the reward is provided right there. Okay? And here, so this suggests that dopamine activity is linked to the expectation of reward. And here we see an example at the bottom where there is a tone, but it's a trick, and no reward is delivered. So the neurons increase the firing rate when they hear the tone, but then you see a slight depression when they don't get the juice they expected, or the water they expected in this case. So this and many other studies suggest that the activity of dopamine neurons is strongly tied to the expectation of reward. And these neurons fire in proportion to the value of the stimulus. That is, the greater the expected value of the stimulus, the greater the release of the dopamine. So all these findings highlighted an interesting puzzle. So the same neurotransmitter, dopamine, is involved in movement control via its connection with movement slowing and Parkinson's disease, as well as decision-making via reward expectation and value-based choice. So could it be possible that these two processes, decision-making and movement control, are linked? And that puzzle is the central theme of my talk today. So when it comes to understanding the brain, there are two types of decisions that are often studied. The first is what to do. For example, do you eat the apple or the cookie? And the second is how to do it. So the choice of the movement that follows. So if you, like me, prefer the cookie, of course, why would you not prefer the cookie? But if you prefer the cookie, does that mean you're going to reach faster for the cookie than if you were forced to reach for the apple? So traditionally, so you never thought about these questions before, but you can think about them on sabbatical. So traditionally, these two questions have been treated separately. But recent results have demonstrated that people will actually reach faster for items they prefer more. So I thought this was super interesting, that the way that people move and the decisions they make may be related. But I realized that to investigate this further, I needed to determine whether there's actually a framework capable of explaining both. So a single framework capable of explaining not just your decisions, but the movements we make. And the framework we proposed is based on the intuitive idea that our choice of action and our movement reflect an interplay between reward and effort. Okay, so how do we make these choices? So a standard approach in decision making is to ascribe to each option, okay, two factors: the reward at stake and the effort required to acquire that reward. So the former serves as a gain and the latter serves as a loss. Now, a major determinant of most movements we make is the effort they require. But despite decades of research in decision making and movement, we still don't have a good understanding of how the brain represents efforts. And that is really the central question of my talk, or of this really research project. How does the brain represent effort? And I hypothesize that the brain represents effort as the metabolic cost of the action. Okay? And if we represent effort as metabolic cost, then this framework, where you consider both reward and efforts, can explain not only the choices you make, but also the movements that follow. Okay? But to move forward with this, we need to know what the energetic costs of movement actually are. And when it comes to locomotion, scientists have been measuring metabolic cost for decades. Okay? And they've observed a consistent relation between the rate of metabolic expenditure and walking velocity. So they've showed many times that metabolic rate increases linearly with velocity squared. Okay. Now, velocity is distance over time, so we can replot this here because I like to plot things versus duration. So this is metabolic rate versus duration, and so you see that if you were to walk 1 kilometer, the longer the duration, the lower the metabolic rate. So metabolic rate decreases with time for a fixed distance. Okay. Now this is for walking, but what about reaching? Okay. So up until this point, there had been no measures of metabolic rate in reaching. Okay. So we thought, let's do an experiment. So my postdoc Helen and I brought 15 subjects into the lab. Well, Helen brought 15 subjects into the lab and had them make planar reaching movements across a range of speeds. Very slow, medium, fast, and very fast. Okay, and as they reached, in each block we measured metabolic rate via expired gas analysis. And this is the data. So this is rate of energy consumption in joules per second, or watts, plotted versus reach duration. So this is the data for a 10 centimeter reach, so it decreases with increasing duration. And now we did 2 other distances, 20 centimeters and 30 centimeters. Okay, so what we want to do is we want to parameterize metabolic rates as a function of distance and duration. So we used an equation similar to what was observed in locomotion, okay, and we fit the data to it. And we found that it fit the data rather well. Now, this is metabolic rate. We want, when I showed you the utility equation, the variable there is not metabolic rate, it's metabolic cost. So it's the total energetic cost of a movement of a given distance and duration. So if we want metabolic rate, metabolic cost, we need to multiply rate by duration, and we get an expression for total movement energy, which looks like this, and explains the data well, as you would expect. All right, so now we have an expression for movement energy as a function of distance and duration, which means then that we can take our utility function here and replace that term for effort with our newly determined expression for movement energy. Okay, so now we have a movement utility in which effort is represented objectively as metabolic cost. Now I want to go back to the data for a minute and highlight something interesting. So it's interesting that there appears to be a metabolically optimal movement duration. So fast movements have high costs, and as you move more slowly, these costs decrease, but as you move slower still, these costs increase again. So there seems to be a metabolically optimal speed. So a non-zero duration that minimizes metabolic cost, or non-zero speed that minimizes metabolic cost. Okay, and this is surprising, but we can obtain an expression for this, okay, for this energetically optimal speed. And so we have a prediction now for how fast someone should reach if they were only concerned with minimizing energetic cost. Okay, and we can plot that prediction here. So this is the duration that minimizes energetic cost plotted versus reach distance. Okay, and then we brought the subjects in, and the same subjects, and we asked them to reach at their preferred reaching speed. Okay, actually we did this before the experiments, and then we did the metabolic testing. So we had measures of the preferred reaching speed at each distance. And we see that the duration that minimizes energetic cost does not predict how fast people prefer to reach. So people reached faster than energetically optimal. Okay, so, all right. So let me summarize what I've shown you thus far. We have measured metabolic cost in reaching and found that it decreases with duration and increases with distance. Interestingly, metabolic cost of walking exhibits a similar relationship. Also, there is an energetically optimal reach speed, but people prefer to reach faster than energetically optimal, okay? Suggesting that there's something other than effort that is influencing a person's choice of reaching speed. So if we go back to this utility function, okay, we see that reward can discount effort costs. So maybe when you're moving to rewarding items, like the cookie, their increased value discounts the motor commands, resulting in faster movements. So do we have any evidence that reward influences the speed of a reaching movement. So, to test this idea, we did another experiment. This is my graduate student, Eric Summerside. He's about ready to graduate. Hopefully he'll defend in a couple months. Fingers crossed. So Eric brought 20 subjects into the lab and asked them to make horizontal out and back reaching movements to 4 targets that were equally spaced around the perimeter of a 10-centimeter circle. And there were no constraints on their accuracy. And in each block of 100 trials, one target, one sector was consistently rewarded, while movements to the other targets were not. Okay? And what I mean by reward is that once they crossed the target would explode, there would be a pleasant sound, and the subjects saw that they had gotten 4 points. Okay? And they didn't get this when they reached to the other targets. So for this subject here, I'm plotting their velocity traces. So you can see the velocity trace when the target is rewarded is in red, and when it's not rewarded is in blue. This is the same target, just in different blocks. You see that when that target is rewarded, the subject reaches to it with a greater peak velocity than when it's not rewarded. And this was consistent across subjects. So subjects significantly increased their peak velocity when reaching to rewarding targets and reduced their movement duration. Okay? So these results suggest that targets with a greater reward, this increased value discounts the motor commands, even though it's only 4 points and a nice sound, resulting in faster movements. So these results support the idea that reward can influence movement, okay, movement speed, but we still need to describe the relationship between reward and utility. So a large body of work in psychology, neuroscience, and decision making suggests that reward is discounted by time hyperbolically. So based on these findings, we're going to represent reward here as alpha, and we're going to discount it hyperbolically as a function of duration, where gamma is the temporal discounting factor and t is the movement duration. And now we're going to combine it with the effort term to obtain our movement utility. And one way to represent utility is to simply take the reward that's temporally discounted and subtract the movement cost from it. Okay, so that's one way to represent utility. But we have found that a utility that does a better job of explaining the data is one in which effort, like reward, is discounted by time. So for now, I'm going to move forward with this utility where not only is reward discounted by time, but so is effort. Kind of think of it as it's the net gain that is being discounted by time. And if I have time, or perhaps in the question section, I can explain to you more the data set, the multiple data sets we found that support this function over a function in which effort is simply subtracted from reward and not temporally discounted. But for now, we're going to move with this. So what we have here is a utility that tells us whether one movement or decision has a higher utility than another. Okay, so that's the one you should choose. So the cookie may have a higher J. But it will also tell you that for a movement of a given distance, its utility is also going to depend on how fast you make that movement. So how fast should you make that movement? Let's look at an example movement here with a distance of 1. So this is a plot of utility versus movement duration. Here's the reward term. Okay, reward is high initially, but it is discounted with time. Here's the negative effort term. Effort is high for very fast movements. It costs you a lot to make fast movements, but it decreases with time. Now, if we add them together, we get a utility, and that utility has a peak. Okay, so very fast movements have a high reward, but they cost you a lot of effort. Very slow movements cost you less, but the reward is no longer as valuable. So this gives us an optimal duration that is neither too slow nor too fast. And together, movement utility and this optimal duration yield a number of predictions. So first, what happens when you add reward, when you increase reward? So here's the utility of a movement with a reward alpha equals 1,000. Great, and there's its optimal duration. Now here is the utility of a movement with double the reward, alpha equals 2,000. And so these equations predict that with increased reward, utility increases, and optimal duration decreases. So you should prefer the rewarding option more. You should prefer the cookie has a greater J, and you should also reach faster to it. Okay, so this is confirmed by the reward studies I described earlier. So in reaching, and it's also been shown in sacads, both in monkeys and in humans. Okay. Now, second, the equations predict the following is going to happen when you have a greater effort cost. So we're going to increase effort cost by increasing mass. Okay, so this is a movement made moving a mass that is 2 kilograms. And here's the utility of making a movement of mass 4 kilograms. Okay, so as you move increasing mass, utility decreases, so you should prefer it less, and the optimal duration increases, so you should move more slowly. Okay, so the question is, can we examine this in the context of movement? So let me rephrase this question. Can a utility where effort is represented as metabolic cost explain mass-based changes in reaching speed? Okay, and this is really a 3-part question. We first have to know what the effect of mass is on the metabolic cost of reaching. Then we need to know what is the effect of mass on preferred reaching speed. And then finally we can ask if metabolic cost can explain mass-based changes in preferred reaching speed. Okay, so let me walk you through this. To answer the first question, we measured metabolic cost as subjects made reaching movements with added load on their arm. Okay, and their arm was supported against gravity. They made 10-centimeter reaching movements to 4 targets equally spaced around the perimeter of a 10-centimeter circle. Okay, and we added 4 different loads to their arm: 2.5 kilos, 4.5, 6.5, and 10.4. And so they would reach for 5 minutes with a constant added load, and as they did so, we would measure metabolic rate, okay, via expired gas analysis. Okay, and within each mass condition, we would have them reach at 6 different speeds. So we would measure metabolic rates at different speeds and different masses. Okay, and here are their data. So metabolic rate on the y-axis versus duration. So as you can see, metabolic rate decreases with increases in increasing duration, what we found previously. And we see that metabolic rate increases with added load. And when we parameterize this relationship as a function of mass and duration, we find that metabolic rate increases with mass to the power 0.7. Okay, so our next question is, what about the effect of mass on preferred reach kinematics? Okay, and again, we tested this directly in the lab. We had 12 new subjects come into the lab and make just horizontal out and stop reach movements to 4 targets, again, equally spaced on the perimeter of a 10-centimeter circle. And in each block of 200 trials, we would add a different load to their arm. Okay, and in this case, we added a mass of either 3, 5, or 8 pounds. And we randomized the order across subjects. And importantly, in this case, we didn't tell them how fast to reach. We just let them choose their preferred reach velocity. So we could just quantify how mass affected their movement velocity. Okay, and these are the average velocity traces across subjects. The black is 0 added mass. The red is 8 pounds added mass. So added mass significantly reduced peak velocity. And we found that, and we saw this across subjects. So peak velocity is reduced with added mass, and movement duration increases with added mass. Right. Okay, so question 1, we measured metabolic rate as a function of added mass. Question 2, we measured preferred speed as a function of added mass. Okay, so we can now turn to our last question, our third question. Does metabolic cost explain the kinematics of mass-based changes in preferred movements? Okay, so here's our preferred movement duration data. Okay, now according to our theory, the effort associated with reaching is specified by the metabolic data, which we can now estimate without any free parameters. Then we can compute the expected duration of each reach by estimating the only free parameter in our utility function, which in this case is alpha, and we set gamma equal to 1. Okay? Now, the circles there are the data with standard error, and the line is the model prediction. And as you can see, it can account for the data rather well. But let's also look at, so movement preferences can be explained by representation of effort as metabolic cost. Okay? But we're also interested in other representations of effort. Okay? So, for example, in motor control, it is often assumed that effort is the sum of squared torques, joint torques, required to generate the movement. So in this representation, effort would increase quadratically with mass, and when we try to explain the data, again, only fitting alpha in our utility function, we see that this representation is inconsistent with the data. There's a much steeper change in movement duration as a function of mass. Okay. Now, another alternate cost is one seen in the study of locomotor preference. So in locomotor preference, when people study preferred walking speed, they find that there is the preferred speed corresponds rather well with a speed that minimizes metabolic cost. So in that sense, the utility there is a utility that is only metabolic cost. Okay, so we asked, well, could a utility that was only represented as metabolic cost, could that explain mass-based changes in preferred reaching kinematics? And the black line there is the prediction. If you were to only care about metabolic cost, that's how fast they should reach. So it actually predicts people should reach faster than they were. Okay, so let me summarize this last study. So we found that people choose to reach slower with added mass, and preferred movement speed can be explained with the utility that represents effort as the metabolic cost of the movement. Okay, so in that experiment, we added mass, but there's an even simpler, more naturalistic way to alter effort, and that's by reaching in different directions. So the human arm has a mass distribution such that it resembles a heavy object when you're reaching in certain directions and a lighter object when you're reaching in other directions. Okay, so in a classic experiment back in 1994, Claude Gaz and colleagues asked subjects to make horizontal rapid movements, 10-centimeter rapid movements, and importantly, they could choose whatever speed they wanted to reach at. Okay, and what's interesting is they found that people would reach at 60 centimeters per second in some directions, but only 30 centimeters per second in another direction. So there was a twofold increase in preferred reach speed simply as a function of the reach direction. And again, these people had no time constraints on their movements. So the question is, can we use our utility equation to consider these observations? So according to our theory, the effort associated with reaching, again, is specified by the metabolic data, okay, which sets the parameters A and C to fixed values. So we use the inertial properties of the arm to estimate the effective mass of the hand as a function of the direction of the reach, okay, and that's how we determined what the parameter M was. Then we computed the expected duration of each reach by estimating the only free parameter in this utility function. In this case, it's alpha, because we set gamma equal to 1. Okay. And the resulting peak velocity is shown here in cyan. So it has a direction-dependent pattern. The velocity was largest for the directions for which the effective mass was smallest. So the direction-dependent speed of reaching movements could be accounted for by a utility in which effort was objectively measured via the metabolic cost of the movement. Now, if this framework is useful, it shouldn't just account for the speed of our reaching movements. It should also say something about the decision-making associated with those movements. So in other words, it shouldn't just tell us how fast to reach for the cookie, it should also tell you that you should choose the cookie over the apple. Now, I showed you earlier that as mass increases, utility declines for all durations, okay? That means your preference for a certain option is going to be greater if it has less mass, keeping everything else constant, okay? So the difference in utilities should predict the probability of choosing one option over another. So we tested this prediction. So Natalia Dunskaya and colleagues a few years ago instructed subjects to make a 15-centimeter out and back movement in any direction. Okay? But they were not provided with a target. Okay? So you just have to reach out 15 centimeters. You could reach in any direction you like. Okay? So their choices are described by a probability distribution shown here for the left and right arm. Okay, so as you can see, there are some directions that are more preferable over another, okay, that were chosen more frequently. And we can predict these probabilities with our framework via movement utility as a function of reach direction. Okay, so for each possible movement, we calculate its utility, and then we calculate the ratio of this utility to the sum of utilities across all movement directions to obtain the probability of a reach in a given direction. And then estimating the only free parameter here, alpha, we use the movement utility equation to predict subject choices, and which is shown here in cyan. Okay, so this same utility that described the velocity of movements as a function of movement direction can also describe the movement choices that people made when they're free to reach in any direction. So let me summarize these last few studies. So we found that expectation of reward increases reach speed, a result that is consistent with our utility framework, and subjects preferred to reach to stimuli that require transport of smaller mass, and they do so with a higher velocity. Okay? And interestingly, kind of a side note, people prefer to reach slower in this case than metabolically optimal. Okay, so now I want to take a step back and remind you of this point that I brought up earlier. So an important aspect of our theory is that when you compute utility, okay, both reward and effort are temporally discounted. Okay, now if you search through the literature, you're going to find examples of both types of utilities. One in which reward is discounted by time and you subtract effort from it, maybe even divide it by effort, or you may find a utility where effort as well is discounted by time. And ultimately the question is which function can best account for animal behavior. So let's consider the simple task of producing an isometric force for duration t. Okay, so you're just going to produce an isometric force for duration t in order to acquire a reward. So it's been shown empirically that the energy required to generate an isometric force is linearly related to the force-time integral. Okay, so the utility of this action is going to be that force-time integral, okay, discounted by time, according to our utility framework. Now, if we just consider the case of a constant force, we can simplify that effort utility. So the integral is just f times t, and again, discounted by time. Now, what's interesting about that bottom equation is that as t increases, effort doesn't continue to grow, but it approaches an asymptote. And this makes an unexpected prediction that as the duration of force production increases, subjects will become increasingly indifferent to duration. So as you produce a force for longer and longer, you're going to care less and less about time. Okay, so in 2004, Conrad Cording and Daniel Wolpert performed a pioneering experiment where they asked volunteers to produce a given force A for given time period A, and then to produce a given force B for given time period B. And then they asked them which one did they prefer, which one did they want to do again. Okay, and the data they obtained represented indifference points, where each line connects force-time pairs that subjects felt were equivalent, were equivalently effortful, or equivalently effortful. Okay, so let's take this apart. So this red line here is connecting a series of force-time pairs. What this means is that this point here is generating a high force for a small amount of time, and subjects felt that that was equivalent to generating a smaller force for a longer amount of time, which makes sense. Lower force, longer time, force-time integral, that makes sense. What doesn't make sense is that as the duration increased, the force that they found equivalent did not decrease, but rather plateaued. Okay, so for holding it longer, they held the same force longer, they still felt it was equivalent. And they observed this across a range of force levels. So this is a surprising result, but it's one that can be explained if effort is represented as temporally discounted metabolic cost. Okay, and as shown here. So we did our simulations. So this is our utility function. So you have your force time integral on top for constant force, and it's discounted by time. And as you can see, those force time pairs do not continue to decrease, but they rather plateau. Okay. And here, so if you were to take the standard representation of effort in motor control, which is force squared times time, okay, you would see that those force time pairs are going to decay to 0, as you would expect. Okay? And even if we consider a case where it's just the force time integral, again, we find that those lines decay to 0. Okay? So the inconsistency with the data remains whether forces are quadratically penalized or linearly penalized. The key thing here is to temporally discount the force time integral. So in summary, a consequence of temporal discounting is that the utility of effort doesn't continue to grow, but rather reaches a plateau, an asymptote, and people become more and more indifferent to time with increasing duration. So, okay, let me summarize all the results that I presented. So in both walking and reaching, we found that metabolic rate increases with movement distance and decreases with duration. We found that there's an energetically optimal reach speed, but in that experiment, people preferred to reach faster than energetically optimal. We found that subjects move faster towards a rewarding stimulus compared with a non-rewarding stimulus. They prefer to reach for stimuli that require transport of less mass, and they do so with higher velocities. And finally, as the duration of generating an isometric force increases, the utility of effort did not continue to increase, but rather plateaued, which is consistent with the utility in which effort is discounted by time, okay? But inconsistent with the utility in which when effort is not discounted by time. All right, so in summary, what I presented here is a framework with which to consider both decision-making and movement control under a common rubric. And within that rubric, effort is represented as metabolic cost. We parameterized effort as a function of movement duration, mass, and distance. And both reward and effort are discounted by time. And when we represent effort as metabolic cost and consider this utility framework, then this utility framework can reveal results that are consistent with the maximization of a common utility. So before I end, I want to mention a few limitations. So there's still a lot of work to be done. So we assume here that total movement effort is discounted at the planning stage, whereas there could be a continuous temporal, instantaneous temporal discounting of movements. Okay, and that's something that we're looking into. Also, how can we talk about motor control without considering probability? So that's something we still need to incorporate. So in more realistic scenarios, there's going to be the probability of reward. And in movement, that's reflected through your movement variability or your accuracy. So that's something that we need to consider. We also, while I presented you with that example of the apple versus the cookie, I didn't give you a single experiment that actually did that looked at the choice as well as the speed of the movement. Usually, again, these are looked at independently. So we need to design experiments that are going to look at both the choice and the movement simultaneously. And just to bring it full circle, I want to return to the question of movement slowing in Parkinson's disease. So within this framework, we can make a few hypotheses for why individuals with Parkinson's disease may choose to move more slowly. So for one, the loss of dopaminergic cells may lead to reduced reward valuation, okay, compared to healthy individuals. So they may not find the action as rewarding, okay, which according to our framework is going to lead to slower movements, okay. Also, dopamine has also been implicated in effort valuation as well as reward valuation, okay. So PD patients may actually, with the loss of dopamine, may lead to an overvaluation of effort that is required of the movement, which would, according to our framework, which will also lead to slower movements. And then finally, it could be that the objective effort cost, the actual metabolic cost of the movement, is higher in Parkinson's patients. Okay, and we don't know that, we don't have that data yet. So, and according to our framework, this would also explain slower movements. So these are all questions that we're going to, we've started to pursue. We have a new R01 just in this April. So we're excited to be moving forward with these questions, look at this utility framework, not just in healthy individuals, but also individuals with Parkinson's. So I'd be remiss if I didn't thank the many, many students that have helped me collect this data and put this framework together. So Eric Summerside and Gary Bruning are grad students currently with me at CU Boulder. Megan O'Brien is the postdoc that worked on this study. She's currently at Northwestern, RIC. And Helen Wong started collecting this data long ago with me, and she's an assistant professor at the University of Central Florida. And my collaborator, Reza Shadmir at Johns Hopkins University, we've been working on putting together this framework for a few years now, and it's been a lot of fun. Of course, funding. So with that, I'd like to thank you and be happy to answer any questions.
So I wanted to touch on this uncertainty issue for a minute because you have an asymmetric utility curve, and that would suggest to me if you have some uncertainty in what the cost is going to be or you're planning, that you would want to bias away from the peak optimum if you want to get an optimum average utility out of that. Is there some evidence for, like, can you map on what that uncertainty would be at least? Can we get a sense of, like, you had error bars on like your first graph, so I was curious.
Oh, on the metabolic data?
Yeah, you just lifted that around the optimum. How wide is that compared to the utility curve?
So are you talking which utility curve? The optimal metabolic curve?
The one that showed that
that there's an
you would have some uncertainty around your optimum given variability in your data. That would give you a hint of how sort of the range over which you might expect a typical movement to.
And are you asking whether it aligns, kind of whether their variability kind of covered the metabolically optimal duration?
And then since the curve fell off more steeply on one side, if I had an uncertainty, I'd want to shift that. I want it to be optimal. I wouldn't want to just do an average around that optimal point. I'd want to shift it and get them.
Right. So yeah, no, I mean, it's an interesting point. So the fact that the utility has different slopes on either side of the optimal, and we haven't probed that to look at, their sensitivity to it and their choices and optimal, like whether their choice, how they choose their biases, just to maximize the chance that they're going to be on the optimal. We haven't looked at that at all. But that's an interesting question.
So, you mentioned this in your limitation section about it kind of is happening at the planning stage, estimating these parameters for priority. I was wondering if there was like a learning effect or a novice expert effect where they're better able to estimate these and get a better J sooner, or if experts just have a increased J, I guess, than novices?
Have an increased or maybe less variability. So all of our experiments are, we do them. The reaches are multiple trials because we want to rule out any learning effects, reduce learning as much as possible. So it's an interesting question when somebody performs something suboptimally. First of all, how do you define something as suboptimal? But is that because of increased variability in their movements? Is that because they haven't learned the model, the effort model as well, or they haven't learned the dynamic model of their own limbs as well? So it's really it's just an interesting question overall. So why are athletes so good at what they do? Is it because they have reduced variability? They're more accurate. Let's say someone who Beckham or in the good old days. Is it because he has less variability, or is it because he's better at identifying the optimal? That's as far as I know, there aren't any studies that really been probing that very well. That's a good point.
Yes, in your utility analysis, are you, and choice for the, are you considering explain the rule of darkness?
In which experiments? All of this? All of this, yeah.
Am I emotional?
I never assume humans are rational, never. But we do assume that we bring them in a kind of a base state, yeah. So we don't manipulate affect. We don't scare them. We do have ongoing experiments where we look at the effect of threats on decision making. So we have a controlled condition, low threat versus a high threat environment. But in the experiments I presented today, it's a very neutral lab environment, and we do make the assumption that they're coming in with the normal level of stress you would expect in an undergrad. But
Hello. Do we have a question for everybody?
Did everyone see that?
No.
So the effort you're describing is built on the mechanics. And I'm just wondering if you can comment on the cognitive effort underlying this, because it might be really important, especially for individuals that might be suffering from, it might require more effort for muscle control in a Parkinson's patient and the sensory feedback is poor and so on. So I can imagine lots of factors that would go into the effort other than just the mechanical movement of the arm.
Yeah, no, I completely agree. So when I was starting down this line of research, I looked at a lot of the decision-making papers, and more people are interested in effort, and everybody has a different way to quantify it. So whether it's isometric force or was number of key presses, or whether you use your pinky versus your index finger, one was more effortful. And of course, there's a whole world of cognitive effort literature. So for me, I wanted to start in terms of physical movements, and I thought metabolic cost is a good place to start, but it's no means a good place to keep it there. So there are many things that could vary, right? There's a subjective perception of effort, right? So even there's just that psychological, some 10 joules may feel differently to me than it feels to you, and also depends on my physiological state. It's really interesting that you bring up this control. So we're thinking of experiments now to look at movements that have the same mechanical effort or same physiological effort, but maybe rather they're, instead of using 2 joints, you're using 1 joint. Is it simplified? Is that another form of effort? Is that something you're going to be adding to the equation? So those are all, in cognitive effort, we've been trying to read more about that and look at how people are quantifying that, and also to see whether we can kind of compare it, put cognitive effort on a scale with physical effort, and map them onto each other. Yeah.
My question actually piggybacks off of what you just said about 2 joint, one joint kind of movement, and more about degrees of freedom about which you move.
Mm-hmm.
So it seems like they attach a robotic arm, you're constraining degrees of freedom about which you're able to move.
Yeah.
Like reaching.
Mm-hmm.
And it seemed like when you modeled the movement speed at which was optimal, it seems as though you looked at preferred speed, but you didn't look at preferred movement pattern about which that movement speed might occur. And is that something that you're interested in, or just not interested in, or looking at constraining variable?
What do you mean by preferred? I'm interested in anything related to movement, but what is preferred movement pattern?
If I were to have my arm here, like resting on a table, I would obviously want to move it out and in, not forward and back.
Mm-hmm.
If my arm was here by my side, it might be harder for me to move this way because I might only have certain muscles available versus this way or up and down because my bicep or tricep might be stronger than my external and internal rotators. So I'm saying my preferred muscle activation might be different based on the position of my proximal or distal joint. So my movement pattern or my degrees of freedom about which I'm able to move might determine my metabolic cost or my preferred movement speed. So the preferred speed might change, and that model might be accurate based on whether or not I'm able to move outside that robotic arm.
No, those are all great points. So one thing that may be affecting your decision to use one configuration over another is how accurate you're going to be if you use one configuration over another. So the well-practiced movement, you're more accurate. less practice you're not. So you're going to choose and it may not be dictated by the physical effort that I would measure metabolically. Another interesting question is strength. So if your flexors versus your extensors, or one arm is stronger than another. So maybe it's not metabolic cost in that case, or maybe it's your capacity to produce force. Those are all. So again, it just opens up all these questions. We're providing kind of a base. So here's metabolic cost. Now and there's already more studies coming out, like in this year, finding that, yeah, people don't necessarily make decisions according to, they don't measure metabolic costs, but they say it's not according to metabolic costs. It seems people have a preference for, I can't remember, moving in towards the body versus out towards the body, something like that, which adds another factor.
So touching on one of your limitations in the end about measuring choice and reaction time at the same time, there's been a bunch of experiments in the same vein, decision-making literature, especially in perception. And overall, the finding seems to be that people prefer to be faster rather than accurate. Sorry, the other way. They prefer to be accurate rather than fast. So they tend to be slower than optimal. And this seems to be linking well to some of your findings as well, where unless you correct with the reward function, people are slower than the optimum. Do you find this kind of effect, or do you think that people are very good at those studies didn't measure metabolic cost, for example, so they just rewarded accuracy and reaction time differently in different conditions?
Yeah, I'd have to see how they were determining what was actually optimal. I mean, for our part, what we would do, we would look at so accuracy gives you some probability of reward, right? That's kind of just another way of saying accuracy. So it's how do they trade off that probability of reward with the decay of value and reward with added time. So it's hard to say what would actually be optimal. So I'd have to read the studies to know exactly what you meant. But we would expect that as you reduce probability of reward, then we have very specific predictions for how that utility function would change.
So people have this overall tendency to be slower than necessary.
No, not necessarily. I mean, it really depends on how rewarding it is and what their variability looks like. So, but I'm.
Great. Well, let's take any further questions offline and thank our speaker again.
Thank you.